session. It's my pleasure to introduce Professor Thereza Paiva. She's full professor at Federal University of Rio de Janeiro. She's part of a very traditional group in condensed matter physics in the university. And in addition, she is being responsible for some years now of a very interesting outreach project that in Portuguese is named Tem Menina no Circuito, which in a translation would be Girls in the Circuit. So thank you very much, Thereza, for coming here. And now I pass to you.
So I want to start by thanking the organizers for having me here, and also saying to everybody that I thought this as actual classes. So if you don't, my main goal is to be understood. So if you don't, just raise your hand. Please don't be shy. In preparing this set of classes, I was thinking, what should I talk about, and what kind of approach? And on the title of the school is Emergent Physics in Non-Equilibrium Quantum Many-Body Systems, but so it happens that I don't work with anything that's out of equilibrium, so I won't be talking about this at all. And my plan is to talk about different instances where we have emergent phenomena in quantum many-body physics. And there are like a number of things that interest me, and I believe is interest of the interest of many people around here. Quantum phase transitions, magnetism, transport properties, topological properties, and so on. And just to give you a hint of what I am going to talk about today, last week I was here in another school, which is the School of Light and Cold Atoms. So it's very hard for me not to talk about something I've just, prepared 4 classes about. And so I just want to start with that. And this field of cold atoms is a field which had a very intense activity over the last 30 years. And it was kind of interesting to see that the school was this year that we celebrated 30 years of the first Bose-Einstein condensate. And 30 years from the starting point, which is this June, also we had this major breakthrough, which is this paper, which is on the right-hand side here, where cryogenic temperatures was achieved in cold atoms in optical lattices. And so what does it have to do, with strongly interacting systems? And I will try to show to you today that we have possible different platforms to study interacting systems. And cold atoms is one of them, and materials that probably this audience here is more familiar with is just another platform, real materials. So I had to make choices about the things I'm going to talk about. And I think the back panel of everything that I'm going to talk about are, strong correlations. This is what I work with, and I have chosen different things that, different topics related to strong correlations. So I will talk about quantum phase transitions and magnetism, superfluidity, and also topological properties, but all of them together with strong correlations. And so I have separated the 4 classes this way. So today I'm going to talk about the platforms for strongly interacting systems, and I'm going to talk a lot about cold atoms and optical lattices. Tomorrow I'm going to talk about thermoelectric properties. No, not tomorrow, after the coffee break. And tomorrow about topology and correlations. And after that, I have discussed with the organizers about what should I do on the tutorial. And I planned something which is kind of outside the box. So the idea is I thought, what are the things that I would have liked to know when I was starting my career? And there are some, lots of things that I thought about, and maybe I think I can share with you. And so the tutorial is going to be kind of different, but I think maybe useful. I hope useful. And once again, I expect you to interact with me, especially during the tutorial, but also today. So for now, I'm going to address then the platforms for strongly interacting system. And the summary of this part of the afternoon is what I've written here. So I'll mention cold atoms and optical lattices. And then I'll discuss the Hubbard model that can be modeled in optical lattices, but also in materials. Subir mentioned this in the morning. And then I'll discuss Koster-Lithaus phase transitions, the universality class, and this can also take place both in spin-imbalanced systems and also with systems with attractive interactions away from half-filling, and I'll mention both. So before talking about what happens when you have atoms in an optical lattice, I am going to mention what happens when you trap atoms. And what happens when you trap atoms depends very strongly in what kind of atom you trap. So here I have two different atoms, lithium-7 and 6, and they look, to me, enormously similar. But, they are both neutral, so I'm only talking about neutral systems. They have the same number of protons, the same number of electrons, and they only have different number of neutrons. And what's the difference? And the difference is all the difference, because in the first one, lithium-7, we have an integer spin, and this makes it a boson. And in the other one, lithium-6, we have half integer spin, and this makes it a fermion. And in these systems, the most commonly used bosons are lithium-7, rubidium-87, and potassium-39. And on the other hand, lithium-6, potassium-40, and of course, electrons are not trapped in optical lattices, but they are fermions, and they behave similarly. I hope you get to understand how. So in this case here, we are restrained. We have to obey Pauli exclusion principle, and the physics is completely different. Here is a sketch of what happened. So that first Bose-Einstein condensate was made of rubidium atoms, and it was pretty much like that. You have all the level here, and as you cool down, you bring your atoms to the ground state, and you have a condensate. On fermions, on the other hand, you cannot have that because of Pauli exclusion principle. So what happens here is if you have spin up and spin down, you have each one in each level, and you have a Fermi degenerate system here. So they behave very different because of statistics alone. So one thing that is curious, this is some data about these experiments, how cold it was, how long it lasted, but I'm interested here in density. And this is a very dilute system. And just some numbers here, if we compare to metals, that is something we study very often in condensed matter systems, it's kind of 10 order of magnitudes less than in this condensate. And if we look into a mole of gas in the standard temperature and pressure, also much diluted. And here's just semiconductors to give you a flavor of how dilute the system is. And why is it important? I'll come to it in a minute, but let me just say that a couple of years after the Bose-Einstein condensate was achieved, the degenerate Fermi gas was achieved. I don't have, a figure as nice, but this is what happened. Potassium atoms into hyperfine states. These two here were studied. All the others were removed from the trap, and we had with an abuse of language that I'll keep using. Atoms in this hyperfine state I'll call spin-up atoms, and atoms in this hyperfine state spin-down atoms, and it's like we had a two-flavor spin system in a trap. And so these are the most commonly used states, lithium-6 and potassium-40, and I'm going to just call it spin-up and spin-down whenever we have two species on a lattice or in the continuum. So the advantage of studying these systems is that we can control the interactions. And so Subir was mentioning this morning that, you know, when you have graphene, the interaction is smaller than the critical U to reach the antiferromagnet insulating phase. And there's nothing you can do. It's a material, and the interaction is whatever it is. And here in the systems, we can control the value of the interactions. So how this is done? So I am drawing here a scattering. Two atoms scatter. The first one comes with a momentum k and is scattered to a momentum k prime. And this is the wave function. You've probably seen this in a quantum mechanics course. This is the scattering amplitude, and you do partial wave decomposition. Nothing different up to here. And the good thing is, as I've mentioned, you are in a very dilute and very cold system, so you can take only the S wave component, L equal to 0, and K equals going to 0. And so we only care about the S wave scattering length, and your cross-section is something like that. And when we have atoms in different hyperfine state, we can tune in a magnetic field, and we have Zeeman splitting. So the down electrons or fermions see this potential here. The up fermions see this potential here. They are displaced because of the Zeeman splitting. The splitting is something like that. And by adjusting the Zeeman field B, we can reach a resonance or leave the resonance, and this makes the fermions interacting stronger or less strong as you reach the resonance. And this was actually measured, so this is the scattering wave as a function of the magnetic field. And what we see here, you know, by tuning the magnetic field, it can be either positive or negative. And when it's negative, we have attractive interaction. So this is a very cool, very nice experiment that was done in the group of Debbie Jean many years ago, where we had atoms in these two levels before turning in the field. And as you turn in the field, they kind of disappear. And they disappear because they bind together and form a molecule. So in this experiment, we had potassium-40 atoms forming a molecule. And this is because you can tune in the interactions and to the value pretty much you want. This has led to an enormous amount of experimental activity in this field. So you form a molecule. The molecule made of two fermions is a boson, and then you try to condensate these bosons and so on. So a lot of things happen. But I am more interested, and I hope you get to see why, in what happens when we have optical lattices. So besides the trap that I mentioned before, there was this parabolic shape that I was showing. You have to confine your atoms somewhere, otherwise they would wander around and you wouldn't be able to do your experiment. You want some periodic potential on top of that. And this periodic potential is achieved by counter-propagating lasers, for instance. So here, if you only have two lasers, when you have counter-propagating lasers, you form a standing wave, pretty much like when you go to a basic physics lab and you have a rope, and depending on the frequency of the rope, you have, you know, a standing wave that has maxima and minima. And the idea is the atoms like to sit on the minima. So that's the exact thing that is happening here. So If you only have 2 lasers, this region here looking like pancakes is the minima, and the atoms like to sit in here. If we have 4 lasers, we have the cigar-shaped regions. But if we have like 6 lasers in all the 3 different directions, then we have something that looks very, very much like a lattice that we see on actual materials. And here is a 3D lattice, and this is like one layer of this 3D lattice, and it has like this eggshell when we go and buy eggs in the supermarket, you know. And the atoms, the blue and red, mean the in one spin state, in one hyperfine state or the other. They like to sit on the minima, and the distance here between 2 minima is given by half the laser wavelength. So this, I think, is beginning to look more like a condensed matter system, where we have a perfect lattice. We don't have disorder here because the laser, you know, is very stable and it doesn't change wavelength. And so it's a very ordered system where we have atoms in 2 flavors. So it's very much like having a lattice with spin up and spin down and electrons. And so this geometry can be tuned in either by detuning the laser or adding different directions. So if instead of, you know, 4 lasers counter-propagating on a plane, we have 6, then we can do a triangular lattice, and here many different shapes. And this was a very nice experiment that has shown, you know, the dispersion of graphene-like material because they had this honeycomb lattice. So you can study the physics of different things emulated in the systems. So here's another lattice that I particularly find interesting, which is the Kagome lattice. It has been studied with bosons, but not fermions yet. So, so what can be done in this platform? So the idea is to study many-body physics with ultra-cold atoms in optical lattice, and all these things and much more can be studied. So quantum phase transition, quantum magnetism, exotic superconductors, disordered system by inputting disorder in a controlled way using speckle noise, topological matter, and so on. So the idea is that we have the same physics in strongly correlated materials, such as this cuprate, and we can emulate the same physics with ultra-cold fermionic atoms in optical lattices. So why going through the bother of, you know, doing this in an optical lattice if I can just pick up some high TC that was, you know, synthesized in somebody else's lab? And the answer is control. With these experiments, we do have an unprecedented kind of control, as we can control the strength of the interactions. We can control the lattice hopping, because the lattice hopping is done depending on the width, on the depth of the potential generated by the laser. So if it is shallow, it's easier to hop. If it's too deep, it's harder to hop. Dimensionality, density, spin imbalance. So this is a platform in which we have very much control of what is going on. And so one of the most studied models within this platform is the Hubbard model. It was proposed in the 60s to study magnetism in itinerant metals, but we know it can go a lot beyond. So let me just quickly go through it. The idea is we have a hopping term that allows particles to jump from one minima to the next one. Pauli exclusion principles prevents us to have 2 fermions in the same site with the same spin. We are considering only 1 level per minima here. We pay an interaction U whenever atoms with different spins meet. And we have a chemical potential that allows me to put and remove particles from my system. And so this is a model that is studied a lot in both contexts, and the reason is because it is the simplest. So we are only considering I think it's, yeah, very light here, but you can see it's a single band, so it's an S band, only one level per minima. We are considering inter-site fermionic correlations, not long-range correlations, only nearest neighbor hopping and no disorder. And the question is whether it's too simple. And maybe for materials it is too simple because maybe correlations go beyond inter-site, maybe hopping go beyond nearest neighbor. But here it's not too simple. Here it's exactly what's being projected in the experiments. So it's kind of allowed for kind of a changing paradigm. Instead of, we have the ability to emulate in the lab a Hamiltonian that we want to study. So how we do that? We replace the atomic nuclei and the core electrons by the optical lattice. This is what gives the periodic potential. We replace the electrons by the fermionic atoms, the electron spins by the hyperfine states, and the Coulomb interactions that are present in electronic system by the fermionic, the Feshbach resonance-induced correlations. So this is how it is done. It looks a lot simpler when I say than if you look at, the actual experiment in the lab. But as I do theory, I can do such a thing. Say it's very simple. It's not. The experiments are they are expensive and they are complicated, hard to build. But anyway, for me, it's easy to say, the idea is simple. So this is how the hopping and you relate to quantities in the experiment, and just highlighting here that it is the S-wave scattering amplitude that can be positive or negative. So the interaction U can be either positive or repulsive, and we are coming to that in a while. So the physics of the Hubbard model is both known and unknown. We know in some regions of the phase diagram, and some regions of the phase diagram are really hard to reach because of, in numerical methods, we have what we call the problem of the fermionic determinant. But at half filling, we know we have a matter-insulator transition and some magnetic ordering. And so let me talk first about the Mott transition. It happens when we have one fermion per site or one electron per site. And when we don't have correlations present, we have a band that is half-filled, and we can, just give a little bit energy and promote electrons, and then we have a metal. But when we have correlations present, this band split, and then we have what we call a Mott insulator, and a charge gap opens. And one way of knowing that the charge gap is there is either by calculating or measuring the compressibility. We see how the density changes with chemical potential, and it's clear here. We increase the chemical potential, and the number of atoms is increasing, and then here there are no atoms in this region, and we increase the chemical potential, and the number of atoms don't increase. And so this thing here goes to 0 whenever we have a gap. And so the first experiments that saw the Mott insulator are from like 2008, and this is what happened. The correlations were turned off, and then we had atoms like 2 per site at most, and then when the interactions were turned on, the number here is the double occupation, that's what was measured, is decreasing as correlations, the interaction strength is increasing. And so we see this band splitting on the experiments. And with the advancement of experimental techniques, we now have what we call the quantum gas microscope, which is optical development to observe in situ with atomic resolution imaging. And this is a major advancement because this is, it was first done for bosonic atoms in 2009, and now in 2015, 6 different groups developed this technology, let me call it that, for fermionic atoms. And this is what happened. So here is the image, and in the down panels are the pixelization image. And we see here what we can clearly see is a MOT insulator with only 1 atom per side. Each of these dots here, blue dots, is an atom, and here the same thing. And just to comment, in this case here, where we see nothing in the middle and nothing in the middle, is not like it's empty. It's that the imaging is fluorescence image. So whenever you have 2 atoms, they are ejected from your imaging system. So here, what it actually means is that we had in the beginning 2 atoms. So you had 2 atoms, and then in this region, only 1 atom, and in the outside, it's empty. So you have a parabolic shape on top of your optical lattice, and the density is not constant, and you see the profile of density in these experiments. So let me make what looks like a very drastic change, but not quite. I'm going to talk about the high TC superconductors. I believe Subi sent a very, very similar phase diagram, because this is the well-known phase diagram of the cuprates. So in this axis here, I have temperature, and here carrier concentration. And so this pink region here is the antiferromagnetic MOT insulator that can be probed in optical lattices by having something just like that, 1 atom per site. And if we reduce the temperature to temperatures low enough, we see the up and down pattern here. And once again, this is the same physics that happen in these planes of copper and oxygen here. And so just one comment, these systems are, the cuprates are systems in which things we like in condensed matter and we learn in basic courses, such as band theory, Landau theory of phase transitions, or BCS theory, they fail. So we have to figure out ways of dealing with that, and I think that's part of the fun. How do we, study systems that go beyond the BCS transition or band theory? And I guess that's the main point of these schools, the emergent phenomena that happen when all these things are not there. So the long-term ambition for people in the field of optical lattices is obviously observe high TC superconductivity in these materials. And why is it interesting at all? Because in the high TCs, we have many things happening at the same time. And so here we can pretty much isolate the different things. So we can freeze degrees of freedom and maybe emulate the Hubbard model. And one thing that we always ask ourselves is, does the Hubbard model have all the physics necessary to explain high TC? And the honest answer is, at least to me, I don't know, because I cannot reach low temperature in my simulations and away from half filling to see what happens in this region of the phase diagram where superconductivity is. So at least from my point of view, I don't know what's in there, and I don't know if the model I am studying has all the physics needed. So it would be very, very nice if some experiment of that model could, see what's going on here and tell me. And so maybe join forces, to have a better understanding of what's going on there. So the problem with these experiments is temperature and cooling. So if we look at what's happening here, as we decrease the temperature, first we reach the MOT insulating region, then we reach the Niel ordering, and of course doping the system, but at lower temperature, we reach the superconducting temperature. So we would have to reach low temperature in the systems to observe this. And one interesting thing is these experiments in cold atoms are done adiabatically. It's not connected to the environment. So it's hard to know the temperature in these experiments, but it's not so hard to know the entropy. And if the system is isolated, whatever the entropy was in the beginning, it's still there in the end. And so we kind of know the entropy for the Mott insulator is L log 2. And the Néel temperature is below, and D wave TC, we don't know. So here, the Néel temperature, we do know in 3D for the Hubbard model, but the D wave critical temperature, we don't. I thought you were going to ask a question, Reinaldo, because anybody has a question? So I am moving now to a related subject, which is the Kosterlitz-Towles transition. And this was studied in spin imbalanced systems. So the idea was put on an optical lattice a system with a given number of up spins and a different given number of down spins, and these numbers are controllable. So this has been studied with varying polarization, and the polarization went from 0, which is the balanced system, to a very high, 0.9. If we had 1, we would have a completely polarized systems with all the particles spins pointing in one direction. So this is the equivalent of having a Zeeman field in the Hamiltonian. And the idea was measuring the spin components either along the z direction or perpendicular to the z direction along the plane. And this was done in 2D. And so this is what's observed. So here is the spin-spin correlation function. In yellow, what happens along the z direction, and in blue, perpendicular. And here, in this, when it's 0, is the unpolarized system, and here, close to 1, the completely polarized system. What we see first is that if the system is not polarized, then blue and yellow are the same, so the system is isotropic. We can have the spins pointing in whatever direction, and the intensity is the same. Oh, and the symbols here, the closed symbols, either blue or yellow, are experimental data, and this shaded region is simulations. Why we have a shaded region? This is interesting. Experiments cannot tell what is the temperature in their experiment. This is kind of funny, but there is no thermometer to measure low temperatures in an optical lattice. So what happens is theory gives them the temperature. So there are calculations in a range of temperature, which is this shaded area here, that goes from 8.4 nanokelvin to 12.7 nanokelvin, so it's really cold. And with this, we can pinpoint the temperature of the system. So here in the down part of this panel, we have near neighbor correlations, and if we have antiferromagnetism, each one is pointing in each direction, in different direction, and if it's negative. And here is next near neighbor, so it's across the diagonal. If we have something like that, so this is positive, and this is negative. So this is what is showing there. But we see clearly that along the z direction, it falls to 0 faster than in plane, both here and in the next near neighbor. And so we can measure some anisotropy factor, which is simply 1 minus, the z divided by the perpendicular contribution. And if this thing is 0, then the system is isotropic. And as this moves away from 0, this is becoming to be different than 1, and we are approaching 1 when this goes to 0. So we can see here the system is clearly anisotropic when we introduce polarization. This is all done at half filling. And so the image that emerges from this is that when we have 0 field, we have an isotropic system where the spins can point in whatever direction they want. But when we move here towards the polarized system or in the presence of a magnetic field, we start to see that the spins can't in the XY plane. They don't want to be, as shown here. They don't want to be perpendicular in the Z direction. They want all to lie down on the plane. And we have canted antiferromagnet. And so when this isotropic behavior is broken down, we can enter a Koster-Litau's transition. I'll show this more in a bit. And what happens is the critical temperature, which is 0 when we have the isotropic case, moves away from 0, and we have this dome-shaped region here. The only bad thing is this gray region here shows the temperature where the experiments were made. So the experiments were still at a higher temperature than the needed to actually observe the Koster-Litau's transition. Now I'm going to move to attractive interactions, and I'm going to show we have exactly the same physics as we do have here. So this is, I mentioned before, we had the physics of the repulsive Hubbard model where we had localization given by U and itineracy given by T, and these two things competed. But when we have attractive interactions, what we do is pair coherence, superfluidity, and BCS and DEC behavior, and we also have some competition. And so one thing that is also very interesting, the attractive Hubbard model is being studied since the 80s. And back then, what people used to do is, oh, let's postulate we have an attractive interaction because the interaction is on site. And it doesn't matter where it comes from. Let's just study what happens when we have electrons interacting attractively with an on-site interaction. And here, it's not phenomenological anymore. In these experiments, as we tune in the Feshbach resonance and go to the attractive case, it's this that is being emulated in the system. We have an on-site attractive case. And so we can try to figure out a whole phase diagram of what happens. In the repulsive case, we have some antiferromagnetic phase with repulsive interactions that, you know, and a mod insulating as we increase the temperature. And here is the normal case. While here, in the attractive case, we have superfluidity in this region, either BCS or BC, and here a region of preformed pairs. And so it looks very, it was drawn very symmetric for a reason, because this system map on each other. I don't want to make too many calculations here, but I think if you've never done something like that, it's very interesting to see, is the spin down particle hole transformation. So what I am doing here, I am picking up a spin down destruction operator, and I am turning it, replacing it by a spin up operator. And here the same with the the up doesn't happen anything at all, and the down spin, I turn it into a creation one. So the bars are the transformed, and the C's without the bars are the original ones. So I pick up the starting Hamiltonian, which is with hopping T, repulsive U, and Zeeman magnetic field, and I do this substitution here. This one, nothing happens, just get the bar on top, and this one is replaced by something like that. And when I do that, I get this Hamiltonian. So the hopping term is the same. The U term, the plus U changes into the minus U. And what happens here, I replace the Zeeman field by, sorry, it went down, but this was meant to be by the side. I don't know what happened in my slide. And so I replace a Zeeman field by a chemical potential. So if I don't have a chemical potential or a Zeeman field, I am at half filling and I have SU2 symmetry, and I have then that case where all the things are isotropic in the repulsive case. But if I have a chemical potential in the repulsive case, it's the same of having a Zeeman field and polarization. So these things are really locked together. There was a recent experiment that probed this symmetry. So this is what happens when this is for attractive interactions in the left and repulsive interactions in the right side. And the squares represent double occupation, and the circles single occupation. So you can see there is a perfect mapping. And so why is it so curious and important, and what is the nature of this Kosterlitz phase transition? So the Mermin theorem tells us in 2D, it works for t smaller or equal than 2, that the number of parameters of our, the number of components of our order parameter is very important. So if the dimensionality of the system is higher than the number of parameters, then we can have a critical temperature that is non-zero. This is, for instance, what happens in the Ising system. In 1D, we can have an ordered state, or in 2D, if we have an Ising system as well, we have a critical temperature that is non-zero. But here, what happens is if we have the number of order parameters, for instance, either the 3 components of the spin or charge or in superconductivity, then this brings the critical temperature down to 0 when we have this SU2 symmetry. So either half filling or spin balanced, in these cases, we have to have the critical temperature going to 0. But when we break this degeneracy, either by a Zeeman field that is making, you know, the Z component have a different energy than the in-plane component, or spin or superconductivity have a different energy than charge density waves, then we have 2 components, the in-plane spin or superconductivity, and we can have a Kosterlitz phase transition at some non-zero temperature. And why this is interesting? Because, you know, experiments don't reach 0 temperature. This is one of the things we know. And so if we want to see this phase transition in one of these experiments, it's useful to be, you know, in this region where it's the critical temperature is non-zero. So either superfluid state with attractive interaction or anisotropic canted antiferromagnetism in the repulsive case. Yes? Sorry, I could not hear you.
So this theorem holds for different type of lattice, like honeycomb, like triangle lattice.
Mm-hmm.
And also, how would be the number of components of this other parameter? It's like spin is 3, right?
Yeah, so
Okay.
spin is 3. And we entered the Kosterlitz phase transition when we break this 3. And we have the in plane having different energy than out of the plane. And maybe here, I have what happens in the attractive case where the SZ component is mapped on charge in the attractive model, and the up and down or in plane are mapped in the superconductivity. So when we have attractive interactions and we are in the symmetry point at half filling, what happens is charge density waves and superconductive superfluidity have the same energy, and then it drives the critical temperature to 0. But once this degeneracy is broken and we have superconductivity separated from charge, what happens with doping? Then we can have a Costa-Littau's transition at non-zero temperature. Is it clear?
Yeah, so I still don't understand what is the difference between this transition and for D upper than N. The last slide.
So
Yeah, so
if D is upper than N, which is, for instance, in the isotropic case of antiferromagnetism, you have the X, the Y, and the Z component, so you have 3 components, and you are into D, and this makes the critical temperature be 0. So the 2D repulsive Hubbard model into D has a critical temperature of 0. You can only reach antiferromagnetic long-range order in the ground state. In 3D, we have a critical temperature. That's non-zero. But in 2D, it's 0 if you have isotropic magnetism. But if you break this isotropy by, placing spin imbalance, for instance, or a Zeeman field, then it's broken and you have, X and Y, and then Z in a different energy, and then you can have a non-zero critical temperature.
So this isotropy will be broken spontaneously, or
Yeah.
we have to, okay. Sorry. Thank you.
More questions? So this is the original phase diagram of the attractive Hubbard model, and I think it's really interesting. You make a whole phase diagram with 2 points, and I think they could do that because they knew a lot of physics, and this is the fun part of it. You don't need to do a lot of calculations, you have to know what you're talking about. So when your system is empty, the point I've placed it there, then you have no particles, and your critical temperature is 0 because there's nothing there. And when you're at half filling, then charge density waves and superfluid are degenerate. So this brings the critical temperature to 0. So you have 0 in empty systems and half filling, and they calculated at 2 different points, and that's it. And so this is a later calculation. It's basically the same phase diagram. This is Adriana's phase diagram from 91. This is I've done this later, and the idea of doing this with more precision is to give data to the experimentalists who are doing this experiment. So they need to know where to look at. And so the idea here is this phase diagram and this phase diagram display exactly the same physics. So this is the repulsive Hubbard model with Zeeman field H, and this is the attractive Hubbard model with doping. These are sketches from experimental data from optical lattices system. So this is the one I've shown with the canted antiferromagnetism, and this dome here is where we have the ordered phase. And here, instead of showing from 0 to half filling, they have reflected this like from half filling to completely filled, but there is a symmetry around half filling, so this is just a specular reflection. And so here, the critical temperature goes to 0 for CDW and superfluid interactions are together. And here they have, the phase diagram that is extremely similar to this one. And just interestingly, the gray marks here show the critical temperature of the experiments. So this is the experimental temperature, and this is what we know from symmetry. And just again, reflecting that it is the same physics. So how long do I have? Like, great. So I want to talk a little bit more about what happens when we have attractive interactions. So I have two slides, two view graphs here. This is a sketch for what happens in the continuum, and this is what happens in the Hubbard attractive model. So it's somewhat similar. Here, this is proportional to the interaction strength, and here as well. I'll come to that in a minute. But here, if you have if your interactions are not too strong, what happens is you decrease the temperature, and pretty much it happens at the same time here that you form pairs, and the pairs condensate, and you reach this blue region here. And here, the same thing. You're in a Fermi liquid phase, a normal metal, and then you decrease and you enter straight to the superfluid phase. And while here you have stronger interactions, then you form pairs first, and then as you increase further the temperature, these pairs condense. And here the same thing. You have a phase of uncorrelated pairs, and when you cross this line, you enter the superfluid. So this has been known for a while. And this is some data for what happens here with numbers. So the superfluid phase here is kind of tiny down there, but it's there. Here is the Fermi degenerate region, unpaired fermions, and this is a phase diagram with some numbers we can provide the experimentalists. So in the minutes that I have, I want to tell you a little bit about Rodrigo Fontinelli's thesis work. He was not my student, he was Raimundo's student, but he was in my group, and I'm kind of nosy, so I gave a lot of suggestions of things to do and discussed it a lot. So, and he has these two works that I really like, so I am going to talk about them a little bit. So the first thing we thought we should do is kind of map the whole phase diagram, finding the critical temperature. Why? Because experiments are being done, either, in the attractive case or repulsive case, and it's good to provide good estimates of the critical temperature to the experimentalists. So how this was done? We use quantum Monte Carlo calculations to calculate pairing correlation functions. So the pairing correlation function looks like that. This is B is an operator that creates a pair inside I, destroys a pair inside I, or creates a pair inside I. And we are going to probe how destroying a pair in a given site and creating it in another site that is a distance, and this R is the distance from the first site to the other. And we see here that if beta, which is the inverse temperature, is small, then this falls very fast. But if it's higher, if we're closer, getting to lower temperature, then it starts to fall. And so correlations, pairing correlations are sustained through the lattice. And this is an indication that we are in the critical state. And so we do some finite size scaling. We know that we are in this universality class. We know how pairing correlations scale within this class with the exponent eta, and eta is 7/4 in this class. So we do a collapse. This is the known formula for the the correlation length. And here we adjust TC and A, which are a constant, and the one TC that gives the best fit is the critical temperature. So we do this for different system sizes, different densities, different values of U, and repeat and repeat and repeat. And then we came up with a phase diagram that looks like that. So in this axis here is density, in this axis here is U, and the vertical axis is the critical temperature. These two plots show basically the same thing. It's because it's kind of hard to visualize in 3D. One has U in the x-axis and N is the different points, and the other way around here. But the main important thing we tell is, first, well, we do see that it goes to 0 due to the Mermin-Wagner theorem at half-filling, as expected. And we see here the region which is a higher red, is where the experimentalists should try and do their experiments, because this is where the critical temperature is higher. So it's around U equals 5, and density, here around 0.87, 0.7, and we mapped where these guys should do their experiments. But this is not the only temperature that is interesting. As I have shown before, in some cases we have first a pairing temperature and then a coherence temperature. So calculating the pairing temperature is also interesting. This was done by calculating the susceptibility. Whenever it's maxima, this is where pairs start to form. So we have a value here for the pairing temperature. The degeneracy temperature is also interesting. So this is the stars here is where we cross this curve here, meaning we have a degenerate behavior. And so this is what the phase diagram looks for different densities. So this is, once again, information that experimentalists should be interested. And we can see that the pairing temperature doesn't change very much as we dope the system more or less. But interestingly, the degeneracy temperature changes a lot. So this is something also curious. So one other thing Rodrigo studied is what happens if we have layering? Because, the idea is, what can we do to have a higher Kosterlitz-Taulus transition so that experiments have higher chances of achieving this transition? So if we have, instead of one single layer, 2 layers, does it help? Does it hurt? And he actually looked at cubic lattice, which is the result in blue, and a bilayer. And we see that when we only have one layer is when the hopping along the z direction is 0. We are here, but if we add, another layer, we can increase the temperature a little bit, so maybe it's useful. Yes?
So, strictly speaking, this is not a BKT transition anymore, right?
Yeah.
In 3D, the XY model has like a different universality class, right? So, it's...
Yeah, so the fitting has to be done using a different ansatz, not using the Kosterlitz-Taulus phase transition. I'm not showing all the details, but you're right. This is not in the universality class of the Kosterlitz-Taulus transition.
But you're saying that the critical temperatures somehow are comparable still?
Yeah.
Okay.
So this is what we are showing here. Oops. So this is for a given density. Where we see the difference the most is at half-filling, because at half-filling, we know the critical temperature is 0, but when we are in a cubic lattice, then it's not 0 anymore, so we see a huge increase. And so theory and experiments show different transition temperatures, different temperatures. So just to go back to what we had, here is, the gray area marking the temperature where the experiments are, and it's like 0.4 in hopping units, and we've shown that we are like 0.15 in hopping units. So these guys have to, reduce their temperatures by 1/3 to reach these temperatures, to reach these experiments. But, in this very, very recent experiment in 2025 that I, read just before coming here, he had reached 0.05. So I am expecting, like, in the following days to see some in Nature paper where they have actually reached this case, because there are some, this is in the group of Marcus Greiner, and I know there are other groups that are now studying the attractive Hubbard model. But I don't know if the other groups can go to these low temperatures. But this is something I don't think it's going to take long to be seen in experiments. So just one other thing I think is very interesting is to study the BCS-BEC crossover. So what happens when we change the value of the interaction, make the system more or less attractive, and go from one case to the other. One way to study that, I mentioned to you that in one case we have preformed pairs that correlate and as we decrease the temperature, and in the other case we have pairs that form and condense at the same time. So if we study pair formation, we can see this taking place. So this is the statistics, the distribution of the double occupation. And we see here that if we have, this is the density, quarter filling, very small u, we have not very much pair formation. It falls very fast, the number of pairs, u equals 4. But here, you know, at equals 5, we start to have a peak here at the tail of the distribution, and we start to have pair formation. And here, for larger densities, we start to have this pair formation before. So is there any other thing we can look into to see what's going on? And so we looked into Fermi liquid behavior. This is a cartoon. I think it's cute. You know, the idea of having a real particle and a quasi-particle. And so how do we probe what happens when we have Fermi gas? It's very clear. We have here the the fermion momentum, and we know it's occupied below and unoccupied above. But here, when we have this scale of interaction energies, and we use the quasi-particle weight, which is this distance here, this amount of vertical line here to measure, you know, our quasi-particle weight. And if it is close to 1, we are in a Fermi liquid. If it is very, very small, we are not. And this is how we probe. This is something that is achievable, calculatable, if I may use this word, through quantum Monte Carlo. And so we sat down and did the calculation. And so here is the quasi-particle weight. The dots just mark what happens in the critical temperature. So we calculated the quasi-particle weight for different values of U as a function of temperature, and this is what happens. But another interesting thing is what happens with the Fermi surface. So in yellow here is a field region, and as I am increasing the interaction strength, this is fading away, so the idea of a Fermi surface is kind of fading away with increasing U. So the Fermi liquid character is lost when I go from small interactions to strong interactions. Yes?
So is this really enough to call it a not, or like, well, I don't know, like, many things can be not a Fermi liquid, I guess, but I mean, this looks like the behavior in the underdoped regime of the cuprates too, right? Because if you take a single copper oxygen plane in the underdoped region and you wanted to do ARPIS on it, you don't see it, but you still don't call this a non-Fermi liquid, right? I mean,
yeah, so
it's just like not coherent spectral peak, right?
Yeah, so there are other reasons. So here we see that the quasi-particle weight is smaller than 1. So this is also an indicative of non-Fermi liquid behavior. So these two things together are pointing to a non-Fermi liquid behavior.
But I mean, isn't Z comes from expanding about the quasi-particle energy? Isn't this already indicative of having a quasi-particle there? I don't really understand how a small spectral weight,
Yeah, so you can
Yes.
think about, yeah, if this is going, you know, to be very, very small, it's like your quasi-particle is disappearing. And here it's not disappearing, it's smaller than 1, but, you know, we can see here, you know, the larger U, the lower the curve gets. And this is when you're having this blurred region here. So as you go from small U, you have, you know, a very well-formed Fermi surface and a quasi-particle wave that is around, you know, 0.7 to a Fermi surface that is disappearing and a very small quasi-particle wave. So these two things.
What about the other scaling relations? Like, what about the, for example, the frequency dependence of the self-energy or the width of your quasi-particle peak as a function of temperature? Does this still look like Fermi liquid?
So we didn't. We are not able to look at that with quantum Monte Carlo. So we didn't look into that.
Okay, thank you.
So, but I am very close to the end. So so I have 2 sets of conclusions. The first one is that I wanted to stress that control over the experimental quantities in the system, such as geometry, interactions, hopping, and so on, make optical lattices an excellent platform to study emergent phenomena in condensate matter, although it's not a condensate matter system, and I hope I have convinced you of that. And about this last part, I hope I have convinced you that this degeneracy temperature marks the onset of quantum behavior, that the pairing temperature seems to provide a scale for separations, and the Fermi liquid versus non-Fermi liquid can be seen in momentum distribution. And the idea of strongly bound bosons can be probed by the double occupancy distribution. And we were able to get, you know, the sweet spot for the critical temperatures to provide some guide for experiments in this region. So I guess that's all for now.
We have time for discussion, questions.
Thank you. So, like, I mean, I don't know much about quantum Monte Carlo, but how do you extract the quasi-particle weight? Because you said you cannot look at the width, but the quasi-particle weight is the integral of it. So shouldn't you also be able to look at the scattering rate?
So we do have to do some analytical continuation that is somewhat... so this is what we get in quantum Monte Carlo, the Green's function, in either K or R, and the Matsubara frequencies. So we have to do some inversion of that to get Z.
And do you assume any peak shape?
No.
Okay, but I mean like a pathological example where you have vanishing peak height at least, but it's still a Fermi liquid, as if I just put a static scattering rate and just go to infinity, right? So
so there are regions where we have to be very careful to do that, because if it is very, very small, then we'll have some discontinuities. And using maximum entropy to do inversions is always very tricky, and I agree, there is discussion about that, on how to do that in a very trustworthy way.
Okay, thank you.
So since there is no phase transition between the 2 behaviors,
yeah, it's a crossover.
Yeah, so there's losing Fermi liquid behavior. We can still, since there is no phase transition but still a crossover, we can say that the Fermi liquid theory is not applicable to this, or it is applicable but has like a small error compared to the results.
So the idea whether it's applicable or not is very tricky because, as you mentioned, there is a side where it's not applicable and the another side which is applicable. So along the way, it's the Fermi-liquid behavior is lost. And when do you know when it's lost? So the idea of analyzing the crossover is having some scale of temperature and interactions because, you know, these two play a role. But I would, you know, use it with a lot of caution because of that. In some point, it's going to be lost. And there is no critical line that's going to show you that it's a crossover. So be far away from the crossover if you want to use it.
Thank you.
So my question is about the Feshbach resonance. So from the data and from what you said, I can see that changing the Zeeman splitting, changing the field, you can change the interaction. So my question is, what exactly is the resonance condition? Is it when like the Zeeman splitting equals some atomic transition, or what's resonating here, basically?
Yeah, so the idea is we have the lines of the atoms, and as you tune in your Zeeman field, you have these two. So there is one potential, and you have, you know, the allowed states, and when, you know, you cross one of these lines, then you are in the resonant state. And then this is where the correlations go up, because
More questions?
So why is it so difficult to measure temperature in experiments with lattices?
yeah, I also had a hard time figuring out. Do you know any thermometer that measures a temperature of nanokelvin?
Time of flight is not enough?
Yeah, so to do time of flight, you have to open your trap and let the atoms fly. So in the very beginning, this is how it was done. And but now you don't. When you do time of flight, you know, you destroy your experiment, and maybe you don't want to do that every time. So, but this is what was used in the early days of of these experiments.
Thank you.
More questions?
Thank you for this pretty nice talk. I had a question on the mapping between the attractive and the repulsive case. You were talking about the fact that there was SU2 symmetry.
Mm-hmm.
Because in some case you had like a chemical potential and external field, and the other no chemical
So
potential.
you only have SU2 symmetry when you have no chemical potential and no field. This is the symmetry point.
What physically preserved the SU2 symmetry in one case and not in this in the repulsive case and in the attractive case? Why in some case you need an external potential and a chemical potential, and on the other not physically?
Yeah. So the way I like to think about it is just by thinking of the Mermin-Wagner theorem and the number of components of your order parameter. So in the case of the repulsive interactions, if you have an isotropic interaction, all the components, the X, the Y, and the Z components of your magnetization will be the same. And thus, you have three components. So if you manage a way to break these three components having the same energy, which is achievable by using a Zeeman field, then you break this, and then you only have two, and then you can enter the Kosterlitz-Taul's universality class. And in the same way, in the attractive case, you have superconductivity, which has 2 components, and the CDW, which has 1 component. And when you have no doping, they are all degenerate. When you dope, you separate the charge density wave, and then you're left with 2 components, and then you can enter the Costa-Litau's universality class.
Okay, thank you.
More questions? One curiosity about as you showed, you could use different elements to construct the optical lattice. The important thing is that they have 2 levels so that they can be 2-level systems. But
Yeah, 2 spins.
2 spins. But beyond that, there doesn't...
Yeah, so in the school of, the cold atom school, where I had 3 classes to talk about it, I've discussed recent experiments with SUN. So instead of having 2 hyperfine states, they had like 3, 4, 5, 6. So it's a whole new physics that can arise when we go beyond 2.
Different phase transitions.
Yeah, so this is like very, very recent. So they have put this in the lattice and probed near neighbor correlations and shown, how different it is when you have SU2 in 1D and SU3 in 1D and SU2 in 2D. But, I think it's an exciting possibility to see what happens in years to come.
Hi, my question is about a little bit about the numerical side of this. So when we talk about QMC, what kind of variant of this Monte Carlo that you're using for these samplings that you have for these, we just randomly sample all of these and just we do the Monte Carlo, right? So how you do this numerically?
Yeah, so I didn't say much about the numerics because I've made choices, like I mentioned in the beginning, and I wanted to talk more about the physics and less and almost nothing at all on how the simulations were done. But when you do quantum Monte Carlo, what you do is you do a Hubbard-Stratonovich breakup, and then you introduce, in some cases, some people use continuous variables. I use Ising-like variables. And then you do the simulations in these Ising variables, and the price you pay is you introduce an extra dimension, so imaginary time. And then you do the simulations. And so this is a very short for what this is done. We can, discuss it some more.
Is this the only way, or we can do diagrammatic kind of this
There are many, many different implementations of quantum Monte Carlo. The one I use is the one that does, it's either called auxiliary field because we use, an Ising-like auxiliary field, or determinant because we write matrices and we calculate determinants. It's all based on green functions. Actually, we obtain the green functions and then we calculate whatever we want from Green's functions, and then it can be in real time and in imaginary time. And then when they are in imaginary time, we have to do some analytical continuation. So, but there are, I could use diagrammatic or projective or other implementations of quantum Monte Carlo.
Thank you so much.
More questions? So let's thank again the first. We come back after the coffee break.